Yeah, more like southeast. There, you didn't think you were going to get all that from just good morning, did you? Got a whole lesson on naming. Oh, good gracious me. Well, good morning, everyone. I'm expecting some people, here we go, to still turn up. So give them a few seconds to kick in. And then we'll get started. Right, that's much better. Well, I'm going to just do a quick recap of some of the antiderivatives that we've already done. I'm then going to show you a couple of little pieces so we can finish off this section. And we'll be starting section 5.4, which was our second last section that we need to get done this week. And it's called definite integrals. Sorry, this is definite. It will be called indefinite integrals, which is pretty much the same stuff, but we won't be calculating numbers. We'll be adding plus c to the end of our answer. So in a lot of ways, it's a little bit easier. So here is a whole bunch of things that we know how to find antiderivatives of. We can use that to do something like the integral from 1 to 3. Yeah, let's try and look about something that I haven't done. And I'm going to change that 1 and make that root 3. There we go. Okay, there is a weird looking trig one. What do you think I should do next to get it maybe a closer format so I can start using some of this stuff? Because right now it's not really useful, is it, the way it's written? Any suggestions for what I might do to this expression so that I can end up using
secant of x outside the parentheses.
Okay, so let's see what that looks like. Secant times 2 secant becomes 2 secant squared. Secant times this becomes 4 secant x tan x. And now you've got that. Now, do you see that this is really basically made up of two distinctly different terms? So what I'm going to do is I'm going to find the antiderivative of them separately. So let's focus just on secant squared. Wait a minute. Isn't the antiderivative of secant squared tan x? So shouldn't 2 secant squareds get me 2 tan x's? Okay, let's hide that one. The 4's not an issue. You just stick 4 in front of the answer. Secant tan. Do you recognise that secant tan is in this list? And what's the antiderivative of secant tan? It's secant. So 4 secant tans get me 4 secants. And then you evaluate them at x equals 1 and x equals root 3. And plug in root 3, that's going to be 2 tangent. I don't know why I picked root 3 now. Don't matter now. That guy plus 4 secant root 3. Take away this guy. And all you end up with that'll be a minus 4 secant 1. Now, if I'd thought ahead, I would actually have chosen angles like 0 and pi upon 4, and these would have turned into things, but too late now. And I know that sometimes in the homework, they do that. So you have your function, you convert it to something that allows us to calculate its antiderivative. You turn each of the pieces into their antiderivatives, and then you evaluate them at the start and the finish, and you subtract them. And that's pretty much the process. So far, so good? So what's left? Well, we haven't done the fundamental theorem of calculus part 1, and we will, but we've got this little guy. I believe he's question 1. And we are going to look at what's called an area function. Now, an area function, and this is an example one, looks like this. We're calling the function g of x in this case, and it's equal to the area from 0 to some point called x of a function f of t dt. That's what it's saying up there. This is called an area function. So suppose I wanted to find, as we do down here, the value of g to the 4, right? G at 4, that's it. No, that one there. Then it would be the integral from 0 to 4 of this function. Okay. If you started at 0 and you went to 4, wouldn't you be doing that guy? Wouldn't that be the integral? And this is just a rectangle. So what's that? 4 times 4. So the answer would be 16.
Wouldn't it be 4 times 8?
4 times 8. Did you all catch that deliberate mistake? Yes. Now, suppose you wanted to do g of 8. Well, g of 8 is the integral from 0 to 8 of this function. And that would be the red and the blue bit. Right, I already know this bit's 32, so don't I just need to calculate the area of this bit and add the whole thing up? And that will be the integral from 0 to 8. Well, I know that little bit here is the same as that guy, right? So that's 32. And I know that this fella here is 8 and this fella's 4. So what's that? 2 times 16 is also 32. So I get 64. Now, if you wanted to do g of 12, can you see you basically, this picture's getting really messy now, isn't it? Wouldn't you just add that bit on? And you'd get the integral. If you wanted to find the value of g of 8, you'd find the area from 0 to 12 of this function. So are you comfortable about how you would complete the rest of this set of numbers? Right. From 0 to 2, 0 to 4, 0 to 8, 0 to 20, 0 to 24. In fact, 24 would be here, wouldn't it? So, what do you have to be careful about when you calculate areas like this piece here from 12 to 24? What do you need to be careful about?
The negative
That's
sign.
negative.
Negative, right? So up to here, the total answer might be 40. But when you start adding these bits, won't it go down and it'll be, 20 or maybe even 10, because 40 take away 30 leaves you with 10, right? So be careful it's negative. And it says in part B, on what interval of is G increasing? Well, I can tell that even though I've not written the answers. As long as you're using values from 0 to 12, won't the area just keep getting bigger? So it will be square bracket 0 to 12, or open bracket 0 to 12, or the reason why I'm putting in 4 answers is I do not know which one of those 4 WebAssign is looking for. I think you'll find out when you try and plug one of them in, but it is 0 to 12 written in whatever version it thinks is the most sensible. What value of x do you think this is going to get a maximum value at? What value do you think the area function is going to hit its maximum?
12.
Agreed. You want to explain why? You're right.
Because when it goes past 12, it's a negative value, so it's taking away the total amount of area.
Right, so it's getting less, right? Exactly. Okay, so that's a one-off question, but be comfortable you know how to fill in the bits and pieces. I think there was a bit after that where it says, here are 4 pictures. Which one of these 4 do you think would match g of x? So we've got little snapshots of the value of g of x, so you could use that as a clue. So I'm making this up, but imagine that g of x looked like this. Then wouldn't your guess be it'd be a curve? So one of the 4 pictures you're going to choose, it's down here. You cannot see it, but it is there. So the next thing we're going to do is called the fundamental theorem of calculus, part 1. Well, let me start by saying there are only 2 questions. They are dead easy, and the fundamental theorem of calculus part 1 is, for the most part, not very useful. Part 2, that's who we've been using for the last day, right? It's very useful, isn't it? Allows us a shortcut way to find the exact area under a curve. But what does this fella do? Well, he says, suppose you have an area function, g of x, and it's equal to the integral from 0 to x of f of t dt. So suppose g of x is the area function, just like we did here. Then it says, then the derivative of the area function is f of x. So what does that look like as a question? Well, suppose I tell you that from 0x, it's the square root t squared plus 1 dt. And I ask you to tell me what g dashed of x is. So if I give you this area function and I say, what would be the derivative of this area function? Do you notice this guy here is essentially who f of t is? So you would be looking at, oops, the square root of x squared plus 1. Suppose you had this area function, 2t, darn it, it's a t, start again, 2t plus 1 cubed dt. What would be the derivative of this area function?
Two x plus 1 cubed.
Agreed? Now, I'm starting at 0 and finishing at x. Do you know if you start at any number, like 10, it's the same answer? And you might think, well, doesn't the 0 have an effect? Not really. When you use the 0, you get a number. And what do you get if you differentiate a number? It disappears. So it really doesn't matter what the start value of a area function is. Their derivatives are still going to be the same, even if you change the start number. So if I started at 5, the derivative would still be this. If I start at 0, the derivative of the area function would be that. And that is called the fundamental theorem of calculus, part 1. And I'm not going to spend a lot of time on it, because that's pretty much all there is to it. So let me see if we can show you. Okay. The 2 questions, at least that are in front of me, can you see that they are using what I just said? Can you imagine what the derivative of this area function is going to be? Isn't it going to be the square root of x plus x cubed? And in this one here, isn't it going to be in brackets, x minus x to the 5, all brackets closed, all raised to the power of 4. Can you see why the fundamental theorem of calculus of part 1 really doesn't do very much useful stuff, right? The guy called part 2 does a lot of useful stuff. We like him because, you know, we can do stuff with him. But there's other versions of that. You could put the x there and the 4 there, in which case that would become a minus. You could change that s to x squared, or that x to t x squared, something else, and it would change a little bit, but not enough to be of any great interest. So, time for us to start our next section. Is there anything from the one that we're just finishing off that you would like me to go over? Anything I've done today that you like clarification?
There's one on 5.3. It was kind of dealing with I remember one of them. What it had a I was dealing with e to the x.
Okay, I'm looking for something that's got an e to the x in it. Is it this guy here?
Yeah.
You see it? Okay, let's look at that one. What's this doing? I've got another screen in front of me. Well, that's weird. Why have you got the answer? I don't want the answer. The answers are distracting. Why is the answer here? Oh, never mind. Let me zoom back to that question, show you how we would deal with it. Right, so we're being asked, I'm writing the question down then and you'll see it in the paper. In my case, it's 9x to the power of e plus 7e to the power of x dx. And we're being asked to evaluate that. So let's see how we could approach that. Well, I'll have my little shopping list over here. I want to buy something. Let's see. There are two different things going on here. There's this guy and there's this guy. Let's tackle this guy because he's easy. Isn't the antiderivative of e to the x e to the x? So the antiderivative of 7 of them is that guy, right? And we're going to evaluate this one at 0 and at 1. So that's a good start. X to the power of e. First thing that's probably thrown you is you've seen that e and you're getting distracted by this one. That is not what that guy is. That guy is just the same as x cubed, x to the 1.7, x to the half, or x to the any number in the universe you want to put there. That is a power rule. Now, the fact that it is e is just a special number. It isn't pi just a special number, right? So e is a special number as well. It's just a number that's so special it gets its own letter of the alphabet. Now, the rule for power rule, isn't it? You multiply by the power and you reduce it by 1. So I'm going to take this fella, multiply by the power, and then I'm going to reduce it by 1. Well, normally you have a number there, like 8, and it becomes 7, right? Or a half, and it becomes negative half, or whatever it is, and you take 1 away. I'm still going to take 1 away, but the only way I can express that is by calling it that.
Shouldn't it be plus?
And I just did the fatal antiderivative mistake. Didn't I differentiate it instead of integrating? So add 1 to the power, divide by the new power. I'll rewrite that. This is what you got. Add 1 to the power and divide by the new power. I also get thrown by e to the x. because isn't e to the x, isn't its derivative also its antiderivative? It's the same thing both ways. Now you plug in 1 here, you'll get 9 over e plus 1 1 to the power of e plus 1, a bit weird, 7e to the 1. If you plug in 0, well, I don't care what that is, you just get 0, and here you get 7e to the 0. 1 to the power of anything is just 1. So 9 over e plus 1 plus a 7e, and that's 1, so that's 7, so you take away 7. And that horrible mess is the answer. It's not a very pretty answer, but it is. Try another version of that. Suppose I wanted the answer from 1 to 2 of x to the pi. Isn't it a power rule? Add 1 to the power, divide by the new power. Plug in 2, you get that guy. Plug in 1, you get that guy. This fella, well, this fella in particular is just 1. And since they share a common denominator, we could probably do that. Okay, that was a good question. Is there any others that we need to concern ourselves before we move on?
Can we do one from a different section?
We are about to start the next section, if that's what you mean.
Well, like from 7.7.
Depends. Is it going to be a big one? If not, you can wait until the end and I can do it then.
Yeah.
Going to be a big one?
It's the Simpsons rule, so it's just a lot of.
Okay, it'll take a while. Right, if you're interested in seeing a Simpsons rule question when we're finished today, hang about for 10-15 minutes, you can watch it, and I'll stick it on the end of this video, so if you want to see it later, you can do that. So all I need you to do is to remind me not to say bye-bye and leave, but to say bye-bye and stay, so we can do that question. That work for you?
Yep, thank you.
Okay. You're welcome. Okay, so that one's weird. I'm going to go and start the next section. And let's see, are we ready to start the next section? Are we cool with that? Okay, we're good. Well, I guess there's good news and there's bad news. The next section we're going to do, which is section 5.4, is called indefinite integrals.
We can't see the screen.
Oh, gotcha. Well, the good news is you already know how to do indefinite integrals. We've been using them to find area under curves for about a day and a half now. What's the difference? In indefinite integrals, you are not being asked to directly find the area under a specific start and finish value. You're only being asked to find what the antiderivative is and stick a plus c at the end. So a very simple example of an indefinite integral would look like this. Do you notice in an indefinite integral there isn't a start number or a finish number? There's just integral symbol blank. That's how you'll know it's an indefinite integral. Well, let's look at what the solution is. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. What does 3 get you again? What's the antiderivative of 3?
3x.
3x. And the big difference is you just say plus c and you're finished. So that's the good news, right? You already know how to do it, right? In fact, in a sort of a way, don't you have less things to do so you don't have any numbers to deal with, right? You don't have to plug in x equals 2 and x equals 0 and evaluate them and, you know, collect terms and make it look pretty and all that stuff. You basically just write an antiderivative and stick a plus c. So what's the hard part? The hard part is that we're going to give you much more difficult functions to find antiderivatives of. That's essentially the hard part. So here goes. I want to find the antiderivative of x. 4 times the cube root of x plus 3 times the square root of x. Now this isn't new, we have tackled this, but this is just a harder version of this, okay? Whenever we see square roots and cube roots, shouldn't our first job be to rewrite them as fractional powers? Because we really can't do the power rule otherwise. So this fella is going to be 4x to the 1/3. And this guy is going to be x to the half. Oh, and by the way, square roots don't have 2's in them. I just accidentally wrote 1 down. You know, if you don't see a number, it means it's a square root. Well, maybe we're ready to go, maybe we're not. Is there anything else that I need to do before I start doing power rules on this?
Distribute the x.
And aren't we going to stick to the rule of making our fractions improper? So we don't call them 1 1/3 and 1 1/2. We call them 4/3 and 3/2, right? At this point here, aren't we ready to find antiderivatives? We're ready for the power rule. Add 1 to the power and you get 7/3. Dividing by 7/3 is the same effect as multiplying by 3/7. 3/7 times 4 gets me 12/7. You happy where the 12/7 are coming from? Second one, add 1 to the power. Divide by the new power, which in this case is 5/2. Dividing by 5/2 is the same as multiplying by 2/5. That's where the 6/5 comes from, plus c. Now, WebAssign might well allow this to slide. They might say, if you type this in, I'll give you the points. But I don't think that's good math, and I don't want you to get sloppy in the way that you write things down. So there is a kind of convention that we follow in mathematics, and my name for it is the style point rules. And the style point rules in this case is you should always make your answer look like the original. So what does that mean? Well, if the original had square roots and cube roots in it, so should your answer. If your original had 5/x cubed, then when you're finished, your answer should be a fraction, you know, like 8/x7, right? It should look the way it started. You don't need to factor things because the plus c kind of screws that up, but you do at least should make it look like the original. So that's why I'm putting this line in. Do you know that x to the 7/3 is the cube root of x to the 7? And x to the power of 5/2 is the square root of x to the 5 plus c. And that's just good math to write that. Just because the software will accept this, well, you do that. Now, I just thought something really horrible. WebAssign might not like that answer. God, it better. I'll be really annoyed if it doesn't. It should. But I guess if it doesn't, you might have to write that one just to get your points. But I'm 99% sure that it will accept that. If it's designed correctly, it should. So that was an example of an indefinite integral. Here's our next one. Okay, that is scary. Agreed? Any suggestions for what we might do to make it look pretty before we even try and do antiderivatives? Because looking at that, there's no way anything over here can be used on this, right? It doesn't even look vaguely like any of these. So we know we're way too early to start using this table. Any suggestions about fixing this, factoring it, whatever, to make it better? Can you see anything, for instance, on the top line?
Could you factor out 7 sine of theta?
Why not? And that would leave me with this guy. And I'm about to write something down, which is true. Somewhere in the 142 world, you were told trig identities. If you thought trig identities had gone and you didn't need to worry about them, they have just appeared like a horrible monster that you cannot kill. Do you remember that secant squared theta is 1 plus tan squared? Because it is. 1 plus tan squared is equal to secant squared. So doesn't that mean that the secant squared on the bottom cancels the 1 plus tan squared on the top, right? There's essentially, they're the same thing. And that's left us with this. Isn't this guy good to go? Right? I am not seeing happy faces here. Secant squared theta is that guy. Okay. If you find an antiderivative of a sine, 7 sine, do you get a 7 cosine or do you get a negative 7 cosine? Which is it? Antiderivative, correct. Plus c, you're finished. If I turned all these thetas into x's, wouldn't the only difference be negative 7 cosine x plus c? If I turned all these thetas into w's or t's or any letter of the alphabet I could imagine, don't you still get the same answer but with a t or an x or whatever letter happened to be used? So the letter, the variable that's being used and the letter that they choose to use it with really don't matter, right? The math is the same, the answer is the same, whether it's an x, a t, or a theta. So I don't think that should bug you. Do you see what I'm getting at when I say the bad news now? We know how to do antiderivatives, so what's the difficulty going to be? They are going to throw some real stinkers, and that's a pretty good stinker, right? That's a thinking man's question.
Hey, Professor.
Yes.
Could you go over how the secant squared canceled out again?
Right. I take this line here and I replace the 1 plus tan squared with secant squared. So this becomes that. They cancel out, and now I'm left with the 7/7 theta. I am using the fact that 1 plus tan squared is equal to secant squared theta. That is from 142. That is an identity that we just need to memorize and have known. So why don't I write down some more of these guys and see how many you can remember? Because who knows what the next one's going to be. Secant squared is that guy. Does anybody know or remember what tan squared theta can be written as?
1 plus cosecant squared theta.
Oh, it's interesting. What do you think? Nope, it's interesting.
Oh,
Last chance. If you came across secant squared theta take away tan squared theta, it would be equal to something. Do you know what it's equal to?
1.
Yeah. In fact, if you only can remember one of them, try and remember that one. Because if you can remember this one, can't you generate these two by doing a little bit of algebra on it? See, if you take this identity, if you add a tan squared to both sides, don't you get this answer? Right, here's one that I think you should know. Of all the identities in trig, this is the one that if you're going to know any, you know that one. You remember sine squared plus cos squared is 1. Then does it not make sine squared a 1 take away cos squared? I mean, if you just rearrange this, you'd get that. What would cos squared theta be then?
One minus sine.
Okay. Now, if you're going to remember one of them, I think you should remember this one, but shouldn't you be able to use this one to get the other two? Have you noticed that for any identity, if you know one, there's 3 of them, but if you know one, you can always figure out who the other 2 are. Double angle identity. The sine of 2 theta is 2 sine theta cosine theta. Really not too much you can do with that. That's probably the only version of that you should look at. There are 3 versions of the cosine of 2 theta. There are 3 versions of the cosine of 2 theta. Can anybody remember any of them?
Isn't like 1 plus sine 2 or 1 plus sine theta?
No, no. Try to think of what that might be similar to. No, it's not even close to that. Not the ones I'm thinking of. I don't think there are others. Last few seconds. Okay, here goes. Another version. Third version. Don't you wish you'd paid more attention and in trig, at least on the identity section. Right. Now, there's going to be others popping up from time to time, but I think I've probably overwhelmed you already with quite a few of them. Most of the ones you need to know are here. There are some others. Why not? Put in one more that just came to me. There is a fractional way of writing the tangent. There's a fighting chance you remember that one. What's the tangent theta equal to? Equal to.
Isn't it like sine over cosine?
It's exactly that, yes. Okay. So you can see here that if there's any kind of trig function involved, you may well, in at least some of those situations, going to have to use one of these guys to make it look pretty. And the one that I know it's ages ago since we've done it now. In this horrible one here, didn't we have to use that guy with secant squared? And that allowed us to cancel it. Okay, I think we're going to spend a few seconds now. Will you go and say hi in the chat so I can take attendance? Okay. Just going to focus for what time we have left on some trig ones. Sine of 2x over cosine x. Can't use this guy. There isn't a sine 2x in this guy. That's the problem. Sine of 2x can be rewritten as something else. It was in my list.
2 sine x cosine x.
Now, do you see something really nice has happened?
You can cancel out the cosine x.
And so all we're left with is this guy, which we can do. We're finished. There's a trick question for you. I'm trying to catch you here.
You can split sine squared into 1 minus cosine and then cancel out the
Or
cosines.
you could do something even quicker.
Those sine squared x, cosine squared x become 1.
What you were saying would have worked if you changed that into 1 minus cos squared. The cos squares would have cancelled, and you'd be left with 1 plus 1, and it would have got you to the same place. So it's not that what you said earlier was wrong, just a different approach. That's all it was. How about this fella? Last one, this one.
You could change the tangent of x, 3 tangent of x to 3 sine of x over cosine of x over sine of x, which should divide out your sine of x.
And you were saying? The signs cancel?
Yeah, sines cancel, yeah.
Right. And I just realized I gave you this guy to do. But this guy is 3 secant x. And I better make the question relevant. So I had to change the question to make it work. So we end up with just 3, right? 3 secant x wouldn't be a good idea because it's not on my list. Actually, secant x does have an antiderivative, it's just not on my list. So if you got to 3 secant x, you just have to go look and say, okay, I need to know the antiderivative of secant x, and you'd find it. Okay, that is it. So if you are interested in 7-7 Simpsons rule, you can hang about. Otherwise, have a nice day, and I'll see you tomorrow.
Professor,
Yes.
when will there be like another date for like getting help with homework other than just this?
Say again, Matthew. I didn't catch that.
Will there be like another date for homework help?
Oh, you mean a time to get me?
Yeah.
The best time for me, because my schedule is just so busy with the classes I'm teaching, is to catch me early in the class. So I'll try and make sure that I get in early each day. So that'll give us a little 10-15 minutes. If I don't make it, we can always tag it on at the end as well. So that would be every day, basically. Come in early and I'll be here, and hang about at the end and I'll be here.
Okay.
Hopefully that'll get it. Yeah, hopefully. Okay, bye-bye to those who are bye-byeing and those who are staying. I need to get set up with 7-7, the Simpson rule question. So that guy has been a thorn in everyone's side, I think. So let me, where the heck is it? Is it gone? Oh, yeah, you can never get things when you want them. And just looking for my WebAssign page. And then I'll go in. What number in 7-7? What question number was it that we are
It's
working on?
question 4, part C.
4C, okay. We are in 4 right now, or I am at least. Okay, and it's the one with the natural log of, and this, the one I've got in front of me says 1 plus e to the x, but it may change because WebAssign does that. Is that the question? Yeah? And does it look like the integral from 0 to 4? I guess I should share it here. So it should be the integral from 0 to 4. The one I've got is the natural log of 1 plus e to the x dx. Now, the way WebAssign works, however, is that you might have 2 plus e to the x or 10 plus e to the x. I'm going to, if you don't mind, I'm going to mute everybody to reduce the background noise. There we go. So if you need to say anything, you just hit the spacebar. Right. So does that, don't need that. Does that look like the guy you want?
Yep.
Okay, so there are going to be 8 strips, which makes this quite a long job, but let's get it done. delta x is b minus a over n. 4 take away 0 over 8. That gets me 0.5. So this is the beginning of the process. Going to go 0, and we're going to go up in 0.5s until we finished. And for every single one of these values of x, we are going to evaluate, in this case, that guy. But maybe in your case, 2 plus e to the x, or whatever it might be, which is what this fella's for. But the question wants our answer to be rounded off to 6 decimal places. That means you better work to 7 decimal places. So if you've been rounding off your answer to 3, 4, 5, you will be wrong. Even if you do the correct process, the answer in WebAssign will say you are not right. So that could be the first mistake. You might say, but I was working to 6 decimal places, and they said 6 decimal places. Yeah, but they want the answer to 6, which means you have to work to 7, because if you work to 6, those rounding off errors could make the last decimal place 2 or 3 units out. And it wants exact answer to 6, not 99% right. And I'm just a couple of, it ends in 7.2 and it should end in 7.4, right? That'll get you wrong as well. So that's another place it may have gone wrong. So I'll clear this fella out, and I'm going to do evaluating this fella. And I have to do it the long way because the numbers are so accurate I can't use my table. So it's the natural log of 1 plus e to the power, in this case 0, but I'm going to call it 0.0. Close
Professor?
the brackets. Yes.
So what worked for me is if you hover over the the numbers, it actually shows you on the bottom right.
If you hover over the numbers.
Yeah, on the if you go back to your table.
This.
On the
In
calculator.
your calculator.
Here, yeah. If I go to table, okay, so I'm on table. I'm going to go 0, 0.5. I'll do the y value. So I have to set this up, and then you can tell me about this hover thing, which is cool because I've never heard of it yet, and I like to learn things. So if I go to second table, what do you mean by hover? What did I do?
So on the press right with the arrow key.
Oh, it's down at the bottom?
Yeah.
In my, cool. Well, you're going to have to trust me. I'm going to have to move it over here so I can write the answer down, right? So this is me writing down 0.6931 Then I'll move into the next one, and it's 0.97407. 1, 2, 3, 4, 5. And 698 becomes 70. Right, 698 becomes 70. Right, the next one is 1.3132617. The next one becomes 1.7014133. The next one becomes 2.12692801. Still a 0 then. Oh, this is cool. This is cool. I like this. 2.5738. 973 becomes 97. And I have 3.048587. 8735 becomes 4. Two to go. 3.5297,504. And the last one is 4.0181. That's 4 digits. 4, 9, 1, 2, 3, 4, 5, 6, 9, 2, 7. Phew. Okay, so you got this ugly mess of a table. Wouldn't this table be able to do L8, R8, trapezoid 8, and Simpsons 8? So you could at least use this table for all those combinations. But we only want to do it for Simpsons 8, right? So for Simpson 8, it's delta x over 3. And the pattern is 1, 4, 2, 4, 2, 4, 2, 4, 1, right? So it's going to be the first guy, 4 times the next guy, 2 times the next guy, 4 times the next guy, all the way to the end. And at the end, it's going to be 4 times this fella and 1 of that guy. Delta x is 0.5 over 3. And then it's 1 of these, 4 of these, 4 of these, 4 of these, 4 of these, or 1, 4, 2, 4, 2, 4, 2. See, I almost screwed up. 4, 2, 4, 2, 1. Now, at this point, it's just really being really careful with an awful lot of digits. And I'm not quite sure. I mean, I can type these numbers in and I can tell you what the answer is going to be because I have it in front of me. But the final answer is going to be 8.804229. And I know that only because it told me on website. Now, all I would be doing at this point would be writing that and going 4 times that, plus 2 times that, plus 4 times that. And about 10 minutes from now, working on the assumption that I never hit 1 digit wrong, or wrote a 9-2 when I should have written a 2-9, or that I didn't miss one of these digits when I was typing it in, and all the other careless mistakes I am bound to make. Can we trust me that that's where we would end up? Now, if you're not ending up there, it is just simply a process of it's dead easy to screw up. And the next time you do it, you'll have screwed up at a different place. Right? It's just, I don't know, it's life, right? Life sucks sometimes. This question sucks, right? It just does. So that's what you will get, at least on this version. The process is correct. I'm assuming that I wrote all of these down, which is no guarantee. I may have actually written one of these down wrongly. I guess that's another place I could have screwed up, right? But if you did it and you were very precise and very careful, this would be the final answer. This guy here, and we would be over. Now, I could physically hit those buttons. I'm not sure what the benefit would be. If I got it right, I would be amazed at how good I was. But I'm pretty sure I would hit the wrong button somewhere in the process from the start to the finish, and I wouldn't get the right answer. So what you might want to do is, if your answer is darn close to this, can you assume that you did pretty much 90% of it right, and it was just a digit somewhere that got missed or changed in some way, and that's why it's not 100% right. Are we cool with that?
Yeah, I think the
Get
problem
out
I did
of
was,
jail free card, right? That's the best I can say.
yeah,
I
didn't
really don't
round
want
the,
to do it by hand
7th
because I know
decimal.
what my carelessness is like, and I have issues with only having one good eye, so I tend to scan badly as well. So I miss a line when I'm typing it in. Any other questions since we're here before we move?
Could it? I had the question that I was answering, or that I was asking earlier was, it was on the evaluating the integral,
Okay.
and so in the numerator you integrated, but the denominator you didn't, but you still canceled that out. Does that mean you're able to do that?
I don't know what your context is. Could you tell me what the question is, and then I just go through it and see what I'm doing? That would make more sense. to me.
Yeah. So it was 3 sine of theta plus 3 sine of theta times tangent
Tan
squared
squared.
all
Right.
over secant squared.
Okay. I did a line, but I just verbalized it. I didn't write it down. So I'm now going to write that line down, and hopefully I'll make it clear. So I pulled out 3 sine theta,
All right.
like that. And then I recognized that this guy was secant square theta. So the next
Right.
line that I should have written down is that line.
Okay, so that means, and so, but you haven't integrated the bottom number?
No, I'm not integrating anything yet. All I'm doing right now is
Oh,
algebra tidying it up.
oh, okay.
And it's only when I get to here, when it's as simple as it can, it's at that point that I then integrated.
Yeah, I missed that. Yeah, I thought, yeah, I think I forgot that we were just changing the identities and stuff like that.
Right. So it was, yeah, changing identities, cancelling, simplifying, all that good stuff.
Okay.
And once
great.
you've got it to a point where, yeah, I can now find antiderivatives, then you do the antiderivative. Very often the antiderivative is a one-line deal. You got an answer and you get the antiderivative. So there might be 6 lines in your working, but only one of those lines will actually be the antiderivative process. All the other lines are probably going to be the algebra to get it to work. Now, and this is trig, but in the earlier questions, wasn't the algebra turning square roots into half powers, or foiling things out, or factoring, whatever it would be, right? Things like that. And we had to do that first.
Okay, great. Thank you.
Okay. Any other questions?
I had a question.
Yes, Martin.
Numerical